They called it a routine dive. Push the nose down, gain speed, line up the shot, pull back. That was the theory, but at a certain altitude and a certain velocity, something changed. The control stick stiffened, the nose continued dropping. The aircraft no longer responded as it should. Nothing was broken. The engine roared normally. The wings were intact. There were no visible failures. The problem was not mechanical. It was aerodynamic. In late 1942, pilots flying high-performance fighters like the Republic P-47 Thunderbolt began reporting dives so fast that the controls seemed to freeze. Some survived only because they activated systems that were never meant to solve that specific problem. What appeared to be a mistake made in panic would later become a clue, and that clue would help aviation understand one of the most dangerous invisible thresholds in flight. The beginning of the Second World War, the principles of flight still felt contained within known limits. Aircraft were faster than those of the previous generation, but their behavior remained largely predictable. If a pilot pushed forward on the stick, the airplane descended. If he pulled back, it climbed. If something failed, investigators could usually identify a mechanical cause: engine malfunction, structural fatigue, combat damage, icing. The chain of cause and effect was tangible. However, as wartime pressure accelerated innovation, aircraft performance began to approach a region of physics that engineers had only partially explored in wind tunnels and theoretical calculations. Engines grew more powerful, propellers more efficient, airframes stronger and heavier. Fighters were expected to operate at higher altitudes and to dive at increasingly extreme speeds in order to intercept bombers or escape enemy pursuit. Speed became not merely an advantage but a survival requirement. And somewhere in that escalation, pilots began encountering a boundary that did not announce itself with smoke or mechanical failure. It arrived silently and without warning. As aircraft accelerated in steep dives, especially from high altitude where the air was thinner, portions of the airflow over the wings and tail began to approach the speed of sound. The airplane itself was not necessarily supersonic, but localized pockets of air were compressing in ways that dramatically altered pressure distribution. Shock waves could form over sections of the wing. The center of aerodynamic pressure shifted rearward. The horizontal stabilizer, responsible for controlling pitch, could suddenly lose effectiveness. The phenomenon that would later be called Mach tuck caused the nose to pitch further downward as speed increased, deepening the dive rather than allowing recovery. At the same time, control surfaces felt heavier, sometimes nearly immovable, because the forces acting against them multiplied with velocity. Pilots described the sensation as if the airplane had entered a different physical environment, one where their inputs no longer translated into motion. The faster the aircraft went, the less authority they seemed to possess over it. This was compressibility in action, and during the early years of the war, it was not fully understood operationally. Reports began to accumulate from various high-performance fighters. The Lockheed P-38 Lightning, for example, experienced severe dive recovery issues at high speed, with some pilots unable to pull out until the aircraft descended into denser air where normal control effectiveness gradually returned. The terrifying aspect was not structural failure, but temporary aerodynamic imprisonment. A pilot could be fully conscious, fully aware, pulling back with both hands, and yet the aircraft would continue downward as if detached from human command. There were cases in which recovery occurred only after thousands of feet had been lost. In others, it never occurred at all. The Republic P-47 Thunderbolt, one of the heaviest single-engine fighters of the war, was particularly capable of reaching extraordinary dive speeds because of its mass and rugged construction. It could absorb punishment, and its powerful radial engine allowed it to operate effectively at altitude. These strengths also meant that, in combat, pilots often relied on high-speed dives either to engage or disengage from enemy aircraft. But as speeds increased, Thunderbolt pilots began encountering the same unsettling reports: stiffened controls, nose-down pitching tendencies, violent vibration, and a sense that the airplane had become a projectile rather than a controllable machine. Contemporary accounts describe dives in which control forces became so extreme that pilots had to rely on trim adjustments rather than direct stick movement to alter the aircraft's attitude. In December 1942, a widely reported incident described a P-47 entering a dive so fast that the controls effectively froze, forcing the crew to use an emergency trim system to regain control and recover. What is significant is not only that they survived, but that their survival depended on altering the airflow indirectly rather than overpowering it directly. That distinction would prove critical. Up to that point, instinct suggested that if an airplane refused to respond, the solution was to pull harder or reduce throttle. But compressibility did not yield to brute force. It required changing the aerodynamic aerodynamic balance of the aircraft. Adding drag, shifting pressure, or modifying trim could alter the airflow enough to restore control authority. In other words, the solution was not strength but understanding. And yet, at the moment of crisis, understanding was rarely available. What pilots had was urgency. The ground was approaching. The altimeter was unwinding. The horizon was tilted at a lethal angle. Under those conditions, decisions were not calculated in laboratories. They were made in fractions of a second by men, confronting the possibility that physics itself had turned against them. What makes this chapter of aviation history so compelling is that the danger was invisible. There was no explosion, no visible structural collapse. The airplane appeared intact. The engine continued running. The only evidence that something was wrong was the growing realization that input no longer produced output. That is a uniquely terrifying failure mode. In combat, a pilot expects to face an enemy. Here, the adversary was the air, behaving according to laws that had not yet been fully mapped. The aircraft had not betrayed its pilot. It had crossed into a region of aerodynamic reality that designers were still learning to navigate. And within that narrow margin between controllable flight and terminal descent, a series of desperate improvisations would begin to reveal the solution. In the next phase of this story, we move from theory to cockpit reality. Because compressibility was not experienced as a concept, it was experienced as vibration, resistance, altitude loss, and the dawning awareness that no checklist had prepared you for what was happening. It is in that moment when control seems to vanish that an action taken out of panic would unexpectedly change the trajectory of high-speed flight. The typical combat dive in a high-performance fighter of the early 1940s was a calculated maneuver. Altitude was converted into speed, and speed into advantage. From 10 or 20,000 feet, a pilot would lower the nose, align the gun sight, and allow gravity to assist the engine in driving the aircraft faster than level flight would permit. In aircraft like the P-47 Thunderbolt, whose mass and structural strength allowed it to tolerate extreme velocities, this tactic was particularly effective. The Thunderbolt could dive faster than many of its adversaries without immediate structural failure, giving it the ability to dictate engagement terms. However, the very qualities that made it formidable also allowed it to enter aerodynamic regimes that few had experienced before the war. As the aircraft descended through thinner air at high altitude, acceleration came rapidly. Indicated airspeed climbed. The altimeter unwound at an alarming rate. The control forces, which initially felt firm but manageable, began to change character. Pilots described a growing heaviness in the stick, not unlike pushing against thickening resistance. This was not the light aerodynamic buffeting associated with approaching a stall. It was the opposite, an increasing rigidity as airflow compressed over the wings and tail surfaces. At certain speeds, shock waves began forming over sections of the airfoil. The smooth pressure gradient designers expected was replaced by abrupt transitions in airflow behavior. Lift distribution shifted rearward, subtly at first, then decisively. The nose began to tuck further downward. This was not necessarily the result of pilot input. Even with neutral stick pressure, the aircraft could exhibit a tendency to steepen its dive. The center of pressure, moving aft, reduced the effectiveness of the horizontal stabilizer. The elevator, tasked with commanding pitch changes, found itself working against altered aerodynamic loads. The faster the aircraft traveled, the greater the compressibility effects became. Control surfaces that were perfectly adequate at moderate speeds felt progressively less responsive. Pilots pulling back on the stick encountered forces that increased dramatically, sometimes to the point that two hands were required. In extreme cases, even maximum physical effort produced little or no visible change in trajectory. The psychological transition from confidence to alarm happened quickly. Combat training conditioned pilots to expect resistance in high-speed maneuvers, but it did not prepare them for total authority loss. In that moment, the aircraft ceased to feel like an extension of the body and instead behaved like an independent mass obeying a different set of rules. Vibration intensified as airflow separated and reattached in unstable patterns. The artificial horizon displayed an angle that grew steeper by the second. The ground, previously distant and abstract, began resolving into discernible shapes. Reports from multiple theaters of war documented similar experiences. Pilots would enter dives intentionally and discover that recovery required far more altitude than expected. Some managed to regain control only after descending into denser air, where shock-induced flow disruptions diminished and normal aerodynamic authority gradually returned. Others did not have sufficient altitude to wait for physics to correct itself. The margin between survivable descent and fatal impact narrowed rapidly once compressibility effects intensified. The sensation was often described as being locked in, as though the airplane had committed to a trajectory that ignored human intervention. In the P-47, whose weight allowed it to build tremendous momentum in a dive, the stakes were particularly high. Its mass meant that once velocity accumulated, inertia amplified the consequences of delayed recovery. Yet that same mass also provided structural resilience, enabling the aircraft to withstand loads that might have destroyed lighter fighters. This duality made the Thunderbolt both capable and dangerous in extreme dives. Pilots trusted its strength, but strength alone could not overcome aerodynamic transition. When shock waves formed over the wing and tail, brute force on the controls did little. The issue was not structural rigidity, but airflow behavior. Imagine the cockpit in that moment, the altimeter spinning downward through thousands of feet, the slipstream noise rising to a sustained roar, control forces climbing beyond normal expectation, the pilot applying increasing backward pressure, waiting for the nose to respond. It does not. He trims nose up, seeking incremental pitch correction. The response is marginal. The dive angle remains steep. Time compresses. Calculations collapse into instinct. Training provides procedures for engine fires, for fuel starvation, for combat damage. It does not provide a simple checklist entry for shock-induced control lock at near-transonic speeds. And then a realization forms, quiet but unmistakable. Pulling harder will not solve this. At this stage, survival depends, not on overpowering the aircraft, but on altering the aerodynamic balance in a way that changes the pressure distribution itself. The challenge is that few pilots initially understood what specific action would achieve that effect. Some instinctively reduced throttle, though at extreme speeds, drag from the airframe already dominated engine thrust. Others adjusted trim more aggressively, attempting to shift control forces indirectly. A handful discovered that introducing additional drag could slow the aircraft just enough to weaken shock formation and restore elevator authority. But that understanding did not arrive through calm experimentation. It arrived through desperation. The dive continued. Altitude diminished with mathematical indifference. The Earth expanded in the canopy. The aircraft vibrated under loads it had never been designed to experience in peacetime flight envelopes. In that narrow band between compressibility lock and ground impact, the pilot faced a decision that would appear irrational to instructors reviewing procedures from the safety of the ground. Yet in the cockpit, with physics closing in, the irrational could become the only available option. In the next part of this story, that option will be taken, not as a carefully reasoned aerodynamic solution, but as a reflexive action under extreme stress. And in that reflex, aviation will uncover something it had been missing. By the time the aircraft had committed fully to the dive, the sequence was already unfolding faster than conscious analysis could keep pace with. The Thunderbolt's airspeed had built to a region few operational. Pilots had explored deliberately, the altimeter unwound with mechanical indifference, marking the loss of thousands of feet in seconds. Control forces had risen from heavy to extreme. The stick felt anchored, as though connected to something immovable, rather than to aerodynamic surfaces meant to command pitch. The nose continued pointing downward at an angle steeper than intended, and every second of delay multiplied the difficulty of recovery. The engine was not overspeeding. The structure was not visibly failing. The problem was entirely aerodynamic, but inside the cockpit it manifested as a terrifying simplicity. Pull, and nothing happens. At such velocities, shock waves forming over portions of the wing and tail altered the pressure distribution so dramatically that the elevator could no longer generate sufficient counter-moment to raise the nose. The center of pressure had shifted aft, effectively reinforcing the dive. Attempts to counteract this with pure muscle only increased pilot fatigue without restoring authority. Some pilots reported that trimming nose up offered incremental relief, as the trim tabs altered the aerodynamic balance of the elevator itself. However, trim movement was slower than direct control input, and at extreme speed even trim effectiveness could be diminished. The aircraft, in effect, had entered a narrow aerodynamic corridor where conventional recovery inputs were insufficient. It is important to understand the psychology of that cockpit environment. Training emphasizes discipline and adherence to procedure, but procedure presumes a known failure mode. Here, there was no checklist labeled near-transonic compressibility. Lock, the sensation was not one of structural breakup or imminent explosion. It was subtler and in many ways more unnerving. The airplane remained intact and powerful, yet it behaved as though detached from its pilot's commands. The realization that altitude was vanishing faster than control could be regained created a compressive effect on time perception. Seconds felt both elongated and insufficient. The pilot's awareness narrowed to instruments, horizon, and the resistance in his hands. In at least one documented Thunderbolt dive during 1942, recovery occurred only after the pilot resorted to systems not normally associated with pitch control in combat. Accounts describe the use of emergency trim mechanisms to force a change in elevator position when direct stick pressure proved inadequate. The distinction between intentional and reflexive action blurs in these narratives. What matters is that the pilot introduced an aerodynamic change significant enough to disrupt the conditions sustaining the dive. In other instances across aircraft types, introducing drag, whether through partial flap extension, dive flaps in later designs, or other configuration changes, proved capable of altering airflow sufficiently to weaken shock effects and restore control authority. The principle underlying these recoveries was consistent. Modify the airflow and you modify the pressure distribution that governs pitch behavior. Now consider the action that would later be remembered as an error. In a high-speed emergency, reaching for the wrong control is not uncommon. The cockpit of a WW2 fighter contained multiple levers within close proximity: throttle, mixture, propeller pitch, trim wheels, landing gear handle. Under extreme stress, muscle memory can misalign. The landing gear lever, clearly not intended for use at extreme dive speeds, introduced something aerodynamically dramatic if deployed: drag, significant drag. Lowering the gear increased resistance, altered airflow around the wing roots and fuselage, and most importantly, reduced acceleration. Even partial deployment could change the aerodynamic equation enough to shift the aircraft out of the most severe compressibility regime. To instructors reviewing such an action from the ground, deploying landing gear in a high-speed dive bordered on reckless. The structural loads on gear assemblies were not designed for such conditions. Yet aerodynamically, the additional drag acted as a brake. By reducing true airspeed and altering local airflow patterns, it could weaken shock formation and allow the elevator to regain effectiveness. In other words, an action considered incorrect in normal tactical doctrine might inadvertently create the very condition required for recovery. What makes this pivotal is not that the landing gear was universally adopted as a dive recovery tool. It was not. The structural risk was real. Instead, what mattered was the insight revealed by the survival. Drag could break the lock. If introducing sufficient drag restored control authority, then engineers could design safer, purpose-built systems to achieve the same effect. The problem was not invincibility of physics but misalignment between aircraft configuration and aerodynamic regime. Recovery from such an event was not graceful. Structural loads during pullout could be immense. Airframes shuddered under stress. Pilots blacked out under high G-forces as the aircraft transitioned from vertical descent to level flight. But survival, however violent, was preferable to impact. Once stabilized, the cockpit would fall into an almost surreal quiet. The roar of airflow reduced, the engine still steady, the instruments gradually returning to normal ranges. Only then would the pilot comprehend the magnitude of what had occurred. He had not simply misjudged a maneuver. He had crossed into a region of flight where established assumptions failed. What transformed these near-fatal episodes into historical turning points was documentation. Debriefings captured details of control resistance, altitude loss, configuration changes, and recovery techniques. Engineers analyzed patterns. Why did added drag help? Why did trim sometimes succeed where brute stick force did not? The answer lay in airflow compression and shock positioning over lifting surfaces. If shock-induced pressure shifts could be disrupted or delayed, control authority could be preserved. The so-called mistake, therefore, was not valuable because it was reckless. It was valuable because it revealed a variable that had not been fully exploited. Configuration as a tool against compressibility. The pilot did not set out to conduct an aerodynamic experiment. He sought survival. Yet in doing so, he demonstrated that the solution to near-transonic dive lock was not superhuman strength, but strategic alteration of airflow. In the final part of this story, we step back from the cockpit and examine how these desperate recoveries influenced aircraft design, training doctrine, and ultimately the transition toward the supersonic era, because the lesson extracted from that dive extended far beyond one Thunderbolt and one moment of panic. It reshaped how engineers approached the edge of the sound barrier itself. The pilot believed he had survived because he reacted quickly. Engineers would later understand that he survived because he changed the airflow. What felt like luck inside the cockpit would become data on the ground, and that data would help aviation cross the invisible wall that had nearly killed. When reports of high-speed dive lock began accumulating, they were not dismissed as pilot error. Too many experienced aviators described the same sequence: steep dive, rapidly increasing control forces, nose-down pitching tendency, ineffective elevator authority, recovery only after significant altitude loss or configuration change. Patterns emerged. Engineers and aerodynamicists recognized that these were not isolated incidents but manifestations of compressibility, effects approaching the transonic regime. The war accelerated analysis. Wind tunnel research intensified. Flight testing expanded. What had been an operational mystery began to receive mathematical treatment. The core realization was that airflow at high subsonic speeds did not behave linearly. As velocity increased, localized regions over the wing could reach sonic conditions before the aircraft itself achieved Mach 1. Shock waves formed unpredictably, shifting the center of pressure and reducing tail effectiveness. This produced the nose-down pitching, moment that pilots described as the airplane tucking into the dive. The solution, therefore, required restoring pitch authority in an environment where conventional elevator input lost power. Engineers explored several approaches. One involved strengthening and refining trim systems to allow greater control leverage at high speed. Another involved redesigning wing profiles to delay shock formation. Most significantly, designers introduced dedicated dive recovery flaps in some aircraft types, small surfaces that could be deployed to increase drag and alter pressure distribution in a controlled and structurally safe manner. The logic mirrored what desperate pilots had discovered instinctively. If you change the airflow, you change the balance of forces. Drag was no longer simply a penalty to be minimized. Under certain conditions, it became a stabilizing tool. By carefully placing recovery flaps beneath the wing, engineers could shift the aerodynamic center forward, countering Mach tuck and restoring elevator effectiveness. The Lockheed P-38, for example, eventually incorporated dive recovery flaps that dramatically improved high-speed control during steep descents. What had once been a lethal envelope became manageable through design refinement. Lessons drawn from wartime emergencies fed directly into post-war research programs that would culminate in aircraft deliberately designed to operate near and beyond the speed of sound. The Thunderbolt itself did not become a supersonic aircraft, but the understanding extracted from its high-speed behavior contributed to a broader aerodynamic awakening. Compressibility was no longer an obscure wind tunnel anomaly. It was an operational reality. The near-fatal dives forced engineers to confront the transitional regime between classical aerodynamics and the emerging science of transonic flow. Within a few years, research aircraft like the Bell X-1 would deliberately approach and surpass Mach 1 under controlled conditions, armed with data that wartime pilots had helped generate unintentionally. The invisible threshold that once appeared as a trap in combat became a frontier to be crossed methodically. It is essential to recognize that this progression did not emerge solely from theoretical brilliance. It emerged from the feedback loop between cockpit experience and engineering analysis. A pilot reporting that the controls froze might not describe shockwave migration or center of pressure shift in technical language, yet his account provided the raw evidence necessary for aerodynamic advancement. Each survival, each debriefing, each damaged but recovered aircraft became part of a growing archive of empirical understanding. Aviation matured not just through equations, but through lived encounters with physical limits. There is a tendency to frame such stories as moments of heroic improvisation. While courage was undoubtedly present, the deeper significance lies in adaptation. The pilot who reached for an unconventional control during a dive did not intend to redefine aerodynamics. He intended to live. Yet survival required altering the aerodynamic state of the aircraft. That alteration revealed a principle. High-speed instability could be mitigated not by overpowering forces, but by reshaping them. Once understood, that principle could be engineered deliberately rather than discovered accidentally. In retrospect, the wrong action was not truly wrong. It was contextually misapplied under normal doctrine, but aerodynamically revealing under extreme conditions. War compressed the timeline of discovery. What might have required years of controlled experimentation occurred in months because operational necessity pushed aircraft to their limits. The invisible wall of compressibility was not broken in a single dramatic moment. It was gradually mapped through events like this one. Each near disaster illuminated a fragment of the boundary. The lasting impact extended beyond World War II. Post-war jet development demanded deep understanding of transonic behavior. Swept wings, all-moving tailplanes, reinforced control systems, and advanced trim mechanisms, all trace conceptual lineage to the realization that airflow near Mach 1 alter stability in fundamental ways. Modern pilots train with clear awareness of Mach tuck and high-speed aerodynamic shifts because those phenomena were documented, analyzed, and ultimately mastered. What was once a fatal surprise became a predictable, manageable aspect of flight, and so the story resolves not in spectacle, but in quiet transformation. A pilot exits a dive shaken but alive. Engineers read his report. Designers modify surfaces. Test pilots validate new configurations. The edge of the envelope expands slightly. Years later, another pilot deliberately pushes past that edge under controlled conditions and survives not by accident, but by preparation. The error that saved aviation was never about pulling the wrong lever. It was about revealing that the air itself changes character at extreme speed. It was about discovering discovering that control can vanish, not because machinery fails, but because physics transitions. Most importantly, it demonstrated that the solution to that transition lies in understanding airflow, not in resisting it. The next time an aircraft accelerates toward the sound barrier and remains stable, responsive, and predictable, it does so partly because someone once entered a dive that did not want to end. In that cockpit, there was no intention to innovate. There was only urgency. But from urgency came insight, and from insight came progress. Aviation advanced not only through deliberate research, but through the moments when survival forced humanity to confront the limits of the air itself.